Good morning. So first of all, I would like to thank Hilary and David and Todd for inviting me. It's been, I've only been here for a week, but it's been really good already. The only problem is that as I talked to people last week, I started adding more and more slides to my talk. So hopefully I will try to keep in time, but basically I want to talk about too many things. So I've kept the title, but it's going to be a bit more, maybe a bit broader than this. Because I would really like to give an overview of the sort of things we have been trying to do with Quadtree-adaptive type techniques, but applied to shallow water, but also to other problems. And so that's work we have been doing with Graham Rickert, John O'Callaghan, and Richard Gorman, mostly also at NIWA. And there's an et al., which is actually a lot of people in also other places, not only in New Zealand. Okay. So the outline, I will give an introduction to, what is Quadtree discretization, and also the ideas about scaling. I think that's something which is important and which maybe has not been talked that much about, is the way these various methods scales, and can you make arguments relating to both the scaling of the numerical methods and the physical scalings? Can you link the two together to actually predict how you can do with adaptive methods for different problems? Give an example for which adaptivity is essential. We have found for small-scale two-phase flows can really help. I mean, there's no debate that it's very useful for this type of flows. I will give a first discretization of the shallow water equations using an implicit linearized, what I call dispersive scheme, which is pretty close to the standard, let's say, ocean models type schemes. I will give another example of discretization using an explicit nonlinear dissipative scheme, so shock capturing scheme. I will try to give an application to something different, which is a spectral, not in the sense of spectral method, but statistical description of surface wave fields, like prediction of swells and things like that. And how a Quadtree-adaptive method can help to do that. And I will try to finish with some comments on the scale distribution of the non-hydrostatic lock exchange problem and how that, that links to adaptive methods. Okay, so Quadtree structure, it's a very simple data structure in effect. So you start with a big square like that, you divide it in 4, and then you choose in which quadrant you are going to carry on doing that recursively. So in this case, when you choose the 2 left quadrants, and then you can choose where you refine like that. So the nice thing about it is that it's a very simple data structure. It's called the tree because there is a clear logical structure, which is a tree-like structure. Okay, you start at the root there, then you have 4 children, and then eventually you have branches which can be of varying lengths. The nice thing about it is that what I use is finite volume techniques. Okay, so the control volume we consider are always the squares here. So we define quantities as average quantities over d squares. The nice things about that, of course, is that if you look at something which is regular, like this, well, it just reduces to classical finite volume scheme on regular grids. So you can reuse many of the discretization techniques that you use on Cartesian grids. You can easily adapt to Quadtree grids. Okay, it's not very difficult. Another nice thing is that, of course, it gives you naturally a tree-like hierarchical description of the solution. So if you are looking at things like trying to do multigrid, on adaptive meshes, then the Quadtree structure gives you naturally the multigrid hierarchy. You can define the solution on each of the levels, and you have a natural multigrid hierarchy, so you can use that to solve elliptic problem using multigrid efficiency, and that's an important aspect of what I will talk about. So okay, you can compare maybe the closest structure that is more usual, let's say in AMR, or I mean basically the original paper from Marsha-Berger and Phil Colella in '89, I think it was, is block-structured AMR. So in this case, in block-structured AMR, what you do is that you embed Cartesian meshes within themselves. So essentially, you have a coarser grain if you want adaptivity, in the sense that usually these meshes have more than one grid point. Okay, so you cannot really represent that with this structure. Okay, but of course you can represent this one with this Quadtree. Okay, so this is finer grain adaptivity than this. Of course, what's nice about block-structured AMR is that the efficiency of one patch is the same efficiency as your regular Cartesian code. So in effect, when you have big patches, you recover the Cartesian efficiency, whereas there is always an overhead for the Quadtree. Okay, so you can't do it. Basically, because you have finer scale adaptivity, it's a bit more expensive. Okay, so one of the problems, let's say compared to fully unstructured grids, is how do you represent more complex boundaries than something which follow the side. So of course there's a classical what I call Lego coastlines, okay? So you can just cut out the mesh like this and then you get coastlines which look like that, okay? You could think like, okay, Quadtree-adaptivity may help a little bit if you use this, because you can refine locally near the coastline using finer cells easily enough, okay? But you can do better than this, and what you can do is you can do Cartesian cut cell type techniques, and that's what we use to represent boundaries. So essentially here, you represent boundaries using second order representation, if you want, so linear cut cell elements, and you can combine that with the Quadtree easily enough. That's a 2D example, but we also do that in 3D. Okay, so something I forgot also about the Quadtree, which is very important, is that refining or coarsening the mesh is costs very little. Okay, you can do that at every time step, and that's what we do in the example I will show. And the overhead is something, or the cost relative to the rest of the solve is something like 10% or less than 10%. Okay, so you can, it's easy to refine and coarsen the mesh. Okay, so why adaptivity? Well, I want to come back to the simple ideas of scaling. So if you look at a Cartesian mesh, and delta is the ratio between your smallest scale and your problem and the largest scale, so your mesh size if you want, well, the number of degrees of freedom is going to scale like this. So a constant times delta to the -4. So why 4 for a 3D problem? Because you have three dimensions of space plus 1 dimension of time. Okay, and this assumes that the time scale is proportional to the spatial scale. Okay, so you may say, oh yes, maybe that's not the case, maybe you can decouple the spatial time set, but I will just assume that for simplicity. So now if you believe Moore's law, okay, computing pair doubles every 2 years, if you combine this with this, you can make a prediction which is something like spatial resolution of climate models, say, doubles every 8 years, okay, it's 2 times 4, so it's 8 years. So you can check if that works. So what I did there, I just took the ECMWF data is from the ECMWF website, and the triangles are from the Wikipedia page of the Metaphysics page. I didn't find the equivalent, so maybe there is some debate on whether that's okay. So I just plotted that, and okay, that's log linear, okay, that's log here and linear here, the scale, and you see that's, okay, resolution doubles every 8 years, actually a pretty good fit on the ECMWF data. And 10 years is the Metaphysics data, okay? So what's interesting about that is that you may say, okay, you put 4, but maybe if you use semi-Lagrangian scheme, then, you have this decoupling between the spatial time scale. True, but what this tends to show is that it probably doesn't quite scale anyway. So you get maybe in the prefactor, you get in the factor C, okay? Maybe you can increase your CFL by a factor of 4, but that's not going to carry on forever as you increase the resolution, okay? You get a constant factor, the C, but you don't change the exponent in effect, okay? It's, there is much more to this curve because of course people do data simulation on top of it and so forth. So I'm not claiming that it's, it's a perfect fit, but still it gives you a sort of idea. The important thing there is that it's the slope which is important. It's not really the prefactor. What really matters is the slope, of course, okay? And the idea is, can you change this slope with adaptive method? I think that's the main message. Rather than just changing the prefactor, can you actually change the scaling, the slope of this thing? Okay, so so these sort of ideas were implemented in the JERIS solver. So it's actually reasonably old. It was first released in 2001. That's a bit of a promotion slide, so okay, I will just describe quickly. It's really a framework to solve partial differential equations on Quadtree finite volume meshes. So you can solve advection, diffusion, Poisson-Helmholtz equations. That's multi-level Poisson, okay? That uses the Quadtree hierarchy to accelerate the convergence. That works quite well. And if you combine them together, you can solve 2D, 3D, Euler, Stokes, Navier-Stokes, Saint-Venant, so shallow water problem. It's finite volume, okay? So the finite volume corresponds to the elements I have shown you before. So you can see that as, if you want, a cell-centered discretization. It's not vertex-centered. It's conservative to some degree. It's mostly second order. It can be third order for advection for advection schemes. It can do complex boundaries with the cut cell technique. It's also parallelized with dynamic load balancing, which is important, of course, when you do adaptivity. And an important thing is that it's free software. So it was released in 2001 as free software already. And it has quite a few users for various problems.
Is this with rotation?
Yes, you can. I will describe. You can have rotation. I mean, you can
and the second order and the conservation. So the conservation is with the mean.
The conservation is conservation properties are. It's mostly certainly mass conserving, and depending on the problem you are solving, it's going to be or not momentum conserving. But I'm not claiming to conserve everything, of course. It really depends on the combinations you use.
And
but
does anything special happen at the non-conforming nodes? I mean, that's the issue why we've never been able to get it to work in climate modeling, is those nodes are different with a lower
I'm not using a vertex-centered discretization. It's really finite volume, and it's finite volume. It's element-centered discretization. So to guarantee conservation of fluxes of mass and momentum, essentially, the only thing you need to guarantee is that the fluxes at coarse-fine interfaces are consistent.
So
and you can do that.
Co-located?
Yes, it's co-located. I will come back to that a bit later, in a bit more detail. So that there are quite a few papers around. That's the papers which basically describe most of what I'm talking about in this talk. Yes, so there's this 2007 ocean modeling paper which I will talk a bit about, and also I will talk about Quadtree-adaptive tsunami modeling. Okay, I will just give an example of something we have been working on for a long time and for which adaptivity works very well, which is not ocean modeling. It's really small-scale, multi-phase Navier-Stokes simulations. So what you have is, that's just an example, that's a photograph from an experiment where you have a small jet of water in air, okay, and the jet is forced. It's what happened in inkjet printers, okay. That's why people studied it in 1971, because they were developing inkjet printers. And what happens is that the jet spontaneously breaks up into droplets. Okay, that's what happens when you open your tap also in a thing of water. What you see, of course, is that it's a typical multiscale problem, because you go from something which is continuous and has a given scale to something which is discontinuous. So here you have pinch-off, so your effective scale is effectively 0. So you have a ratio of scale which is infinite. It goes to 0 because it breaks off. Okay. Okay, I won't give too much detail. It's all the 3D incompressible Navier-Stokes equations, okay, with variable density and variable viscosity, because you have different phases, and also with a sharp interface between the two. That's an important thing. And surface tension, of course, which is essential there. So what does it look like?
So are you doing the interface? Is it what kind of method for the?
Interface, it's volume of fluid, yeah.
Volume of fluid.
Oops, looks my movie doesn't work somehow. Start the right hand side. Sorry, I started the wrong file. Just going to quickly go back. Oop. Okay, that's better. Okay. Cool. So you start with a cylinder, okay, and it's spontaneously unstable. That's only the interface. And what you see, okay, you get pinch off. And you see you are creating smaller scale. You can get the scales get much and much smaller. And then eventually you get pinch off. And you get reconnection into different droplets. Okay? And what the way the interface is represented there is really with the volume of fluid representation. So it's piecewise continuous. That's why you get little discontinuity, little gaps between the interface. Okay? And then eventually you form sets like droplets and so on. Okay, so just to show you a bit more in detail, just going to zoom on the area of pinch off. And now I represent the facets. The facets are the way the interface cuts the octree. In this case, it's octree, so it's 3D. It's the generalization to 3D of the quadtree is octree. And what you see is the spatial resolution evolving. So every time you change color, you double the spatial resolution. Okay, and what I adapt according to the curvature of the interface, which is the natural scale of the problem, is the radius of curvature of the natural scale. Okay, so here it becomes very large radius, so you can use very coarse cells to describe it. Okay.
The solution's radially symmetric. Right?
Pardon?
The solution's radially symmetric.
Yes, in this case it's radially symmetric. Yeah. So you could have done it with an asymmetric simulation, for example, rather than doing full 3D. But of course, I'm just doing it to show it also works in full 3D problem.
But I guess I'm curious. So it's a 3D simulation, but how the facets are. So is that a graphical thing, or I mean, how are we seeing like what appear to be perfect sort of a mesh on the surface, because you're solving.
But it's the what you see here is the facets are the intersections, so planes intersecting the octree mesh. Okay, so you can see. I mean, typically here it cuts just a square, but others will be triangles and so on. So the combination of the intersection of the. Okay. So you see here you have two triangles, for example, evolving. Okay.
So you are using the cut cell technique
This phase is
It's volume of fluid, it's a bit different.
Yes.
You know, it's similar but different. Okay. Well, the main point about this is that, okay, you truly have a multiscale interfacial flow problem, okay, and what you want to look at is the simulation size, you know, in the end of getting this thing. So, okay, that's a log scale here, and that's the evolution of the number of grid points as a function of time. So the equivalent Cartesian mesh resolution is 1,000 to the cube, okay, so that would be 1 billion grid points if you did that on a Cartesian mesh, okay. If you did that in 2D axisymmetric, it would still be 1 million grid points, okay, it would be there. And that's the adaptive mesh solution. So you see that you start with a very low number of elements because the cylinder is very coarse, and then you get to pinch off, typically up here, okay, that's where your radius of curvature is minimal, and you get about 50,000 grid points and then decrease again. So in this case, you gain several orders of magnitude. I mean, we're not talking a factor of 12 5, we are talking about 3 or 4 orders of magnitude in gain, okay? So okay, that's a bit academic, so can you do it for more complex flows, okay, with multiple droplets and so on, which would be much closer to what, you know, complex ocean simulation look like. So that's a recent paper which was done by other people but using JERIS on the back breakup of a falling drop. So that's a recent, just appeared in International Journal of Multiverse Flow. So what you do is that it's a droplet falling in air, okay, and that's the Eötvös number which characterizes the ratio of gravitational acceleration to surface tension forces. Okay, so it's reasonably large, so the droplet is not going to stay together with surface tension, it's going to break up in multiple fragments, which is exactly what happens there. So you can see that as a rain droplet, big rain droplet falling in the atmosphere. What is the resulting droplet, you know, rain droplet distribution? And the rain droplet distribution you get at the end here is controlled by all the breakup mechanism we showed before, and one very important one is the way this liquid filament break up into individual droplets, and that's what we saw before. It's the plateau Rayleigh instability. Okay, that's just one of the mechanisms. But of course, you get shear instabilities. You have Kelvin-Helmholtz type instability. That's what you get there. You also have Rayleigh-Taylor instability, acceleration, and that's the mechanism you see there. But you see that we can capture basically all these processes, and each of these things, like for example this filament breaking up into individual droplets, is actually resolved by the simulation. It's not something which is subgrid scale model in some way. Okay, and for example, I'm just showing you the detail of that, is how you go from there to there, exactly through this process, which is this back breakup thing. You form a back there, and you form very thin interfaces, and these interfaces under surface tension are unstable, and you form this very fine mesh. And if you look even closer, this mesh, you see you form these cylinders, and each of these cylinders is unstable according to plateau Rayleigh instability that I showed before, so it is also resolved using the adaptive mesh. I didn't show the adaptive refinement there. Well, the point about that is that it's a matter of scaling, is that if you use the maximum resolution, it would be 4 times 2048 to the cube, okay, would be 34 billion grid points. And they managed to do this, and they have good comparison also with experiments in terms of droplet size distribution and so on, with about 4 million grid points. And they solved that in a few hours on 256 cores. So clearly for this type of problem, adaptivity is really, really efficient. Okay, so how do you go from small scale Navier-Stokes I showed before to let's say large-scale oceanic flows when you come from, you know, let's say incompressible Navier-Stokes? Well, what I've written here is typically the difference between, let's say, shallow water equations and rotating and incompressible Navier-Stokes in its standard form. So the blue terms are, if you want, the geophysical elements. So you have BU, which is just the vector, the matrix form of the Coriolis terms. Okay, B is just the matrix with off-diagonal terms, which are F. Okay. And of course, what you need to add to the continuity equation is the evolution now of the free surface elevation. Okay, so you replace a pure divergence equal to 0, and you add the free surface evolution. So there is a nice mapping, if you want, between incompressible Navier-Stokes and linear implicit free surface. Is that essentially what you have to solve to resolve this in an implicit way, rather than solving a Poisson equation. You are solving a Helmholtz equation. So you add this term here, and you can use the same multi-level solver that I used before for Navier-Stokes, incompressible Navier-Stokes. You can still use, of course, the embedded solid boundary, cell boundaries. A question is, what are the energy conservation properties of this scheme? Okay, so I'll just give a bit more detail about this. That's described in more detail in the ocean modeling paper. So what we proposed as a time discretization is a semi-implicit discretization of both the Coriolis term, okay, and also of the free surface. Okay, so we do this type of splitting. So this is some implicit. You go from UN to U hat, okay, and you have to invert this system, okay, because it's a linear system which couples both components, of course. And of course you have a first semi-implicit part which is the first pressure correction, okay. And you do that because of course you want to guarantee at each splitting, you want to guarantee at least some of the geostrophic balance, okay. So you need to always consider both the Coriolis acceleration and some of the pressure term. Then you do a classical splitting this way. You can actually show that this splitting is second order in time, okay. So the error you make in the splitting is still second order in time. And then what you get from this, if you combine these two, is that you get an evolution equation for the free surface, which is linearized. That's the red term here. Of course, here we take into account only H0, the base state, but this should be H0 plus eta n plus 1. Okay, so it will be a fully nonlinear problem. So of course, it's much harder. So we linearize, and we get this equation, just the Helmholtz type equation. That's not, it's very similar to what people do when they do semi-implicit integration of the free surface equation in any model already. So of course,
how did you update U at the end? You haven't written down UN plus 1.
It's yeah, you're right. I haven't written UN plus 1, but UN plus 1 is just so it's going to be U star plus the missing pressure correction. Okay, so after the pressure correction, is so implicit. Yeah. Okay. So of course the problem is that to be able to invert the system easily, okay, you need to be collocated at least for the velocity component, okay, because it's in matrix form. If you are not collocated in velocity component, you get full coupling over the whole mesh, okay. So, but if you are collocated, it's just a 2x2 system, so it's easy to invert, okay. So we are collocated not only in the velocity but also in the pressure. So we are using the evil A grid, okay. I know I didn't think it was that evil, and then I talked to Alistair and he said, "Oh, you are using the evil A grid." So I added that in my slide last week. Anyway, of course, classical structured ocean models use C or B grid, okay, they don't use A grid. One of the problems on why it's hard to use staggered discretization on adaptive meshes is that if you want to do a consistent finite volume type integration, okay, that's your standard C grid discretization, okay, U and V. So if you look at the finite volume for U, it's here, okay, and the finite volume for P or for traces is this square, okay. So the finite volume for P or for the traces correspond exactly to the Quadtree finite volume, if you want, Quadtree mesh, okay? But these ones are staggered, of course. So that's fine, you're happy on a regular mesh, there's no problem there. Now, if you start refining, imagine you refine this cell, okay, by just a factor of 2, like I did here. Now what I have here is that still the control volume for this velocity, horizontal velocity component is here, okay, stops in the middle. Then you have the control volume for these two, and of course they are the same, they are squares which are here and here. And these two, so here there's no problem, but you see there's a gap in between. So essentially, you don't get a consistent tiling of space with the staggered finite volumes, which is a bit of an issue. A way around it is to define U not as volume averages, but as surface averages. And then you are fine because it's surface averages over this, and you get a consistent surface average tiling if you want. But there are also issues associated with that. Okay, so that's one of the reasons why it's tricky to use staggered meshes, but there are other reasons also. So of course, collocated discretization causes velocity pressure decoupling. That's well known since Arakawa 1966, but also since Arlo and Welsh next 1964, okay? Which people tend to forget about when they are in the ocean modeling community. And of course, people in the CFD community never talk about Arakawa at all, okay? They only talk about McGrid and Arlo and Welsh, okay? Okay, so it's been known for a long time by everybody. Interesting thing is that there is a classical in CFD extension, a classical way of resolving this pressure decoupling problem for collocated meshes, which is a paper by Rai and Shaw in 1983 in some semi-obscure paper in some conference proceeding, but people still reference that. And it's been reinvented or at least re-examined in the 90s by Almgren and Colella and so on. Probably the first paper is 1996. So it's called a Rai-Shaw interpolation, or it's also called approximate projection method. That's Almgren's terminology for it, but it's essentially the same thing. So what we propose in this ocean modeling paper is to extend this type of technique to the semi-implicit barotropic solver I showed before. So it's all collocated.
This is
so
for the collocated?
Yes. So I'm not going to talk about too much detail because I don't have the time. So the idea is simple enough, is that rather than using the exact, the Laplacian, which is the convolution of your discrete divergence and gradient operators, which will give you a staggered, under A-grid the problem is that if you do this, then you get a stencil for the Laplacian, which is twice as big as the standard 5-point stencil. Okay, you still get a 5-point stencil, but staggered in space. That's what causes the decoupling. The idea is that you don't do this, you forget about the convolution, the exact convolution, and you just use your standard compact 5-point Laplacian stencil in your evolution equation. Okay, so this is not the convolution of the two. The projection is not exact anymore for the centered velocity field, okay, because you don't get exact discrete non-divergence. Okay, so that's why it's called approximate projection. And you can show that it's equivalent to introducing a damping term on essentially the difference between your two operators, the exact one and the approximate one, is like adding a damping term on your pressure mode. So essentially you are filtering implicitly, there is no explicit filter, but you are implicitly filtering the pressure mode, okay? And what you can show, let's say practically, is that this is enough to keep the pressure mode in check. Okay, it's been verified for a wide range of CFD applications, you know, and complex one with source terms, the divergence, and so on and so forth works quite well. An important point too is that you still use a discretely divergence-free temporary staggered velocity field for advection, so that you can guarantee exact conservation properties when you advect things around also. Okay. So the details are in this paper, and also John McGregor, I think we'll talk tomorrow, John, about a better technique, an even better solution on regular grids, but I think it's out to extend on quadtrees, but anyway. Okay, so you can test that, I mean, you know, because people are skeptical, of course, when you say that A-grid can work, so we have done quite a few test cases. So one is a wind-driven circulation on the F-plane, so it's simple enough, you have wind stress on this direction in the up bit, then this direction, and you get rotation, and that's a stationary solution, and that's the free surface elevation is something like that because it's combined with the F-plane rotation. So you get something like that, and you have an analytical solution for of course the velocity field and the free surface elevation. And the important thing, okay, is two things, that of course you need to have a circular ocean, so you need to represent the coastline well enough. And if you have any modes in there, you expect to actually see them because you integrate for a long time until it's stationary. So, you know, any modes going will kill your solution. And that's the results we get for convergence. So we get essentially with that's the comparison, that's finite element triangular grid, I think, from Muir and Thomasé. That's what you get on the C grid with a LIGO coastline, okay? So you get only first order convergence because of the LIGO representation. And so we get second order representation. And of course, there is no computational mode for that. Okay. Another test, which is also in the circular ocean, is a nice test, coastally trapped wave. So again, there is an analytical solution for that. And it's not a Kelvin wave, it's not a Rossby wave, it's not a gravity wave, it's a combination of the two. So if you have dispersion relations in your numerical model which are not exact either for the inertial waves or for the gravity wave, you're not going to get good solutions for that. So it tests both the dispersion relation for the gravity wave and the inertial waves. And yeah, the pattern looks like that and just rotates around forever, okay? So again, you can test the energy conservation properties of the scheme also with that. So we tried it both with constant resolution here and adaptive resolution. So adaptive looks like that because we adapt according to the gradient of the free surface. And so the mesh adapts, so in the sense that these bits, which are more refined, rotate around. So you see that's the actual solution, it's not the analytical solution. So you see there's a bit of noise, you can see little wiggles there, but that's after many revolutions. So again, the computational mode is not, most of the noise actually comes from the cut cell representation, not from the A-grid mode. So you can look at convergence of that. People have done this test with FVCOM, which is, you know, finite volume unstructured, I think, triangular elements, and also with ROMs. So you see that with ROMs, it's not, here what you have is the phase error, and here it's the correlation, so it's the error in the free surface if you want. So you see that with ROMs you get large phase errors, okay, and that's because of the stair-stepped representation of the coastline. And you see that with GRS adaptive or constant resolution get similar results, and we get essentially perfect phase. And also AVCOM is pretty good in This.
Why you're the only person who are overshooting? Why are you overshooting?
Yeah, it's just the way the correlation is computed. So it's essentially the reference state. Different reference, the way you define the reference state is different. So it's not, it's not really important. No, you're right. It looks weird. Okay, so that tested only, let's say, that tested only partly the energy conservation property. So what I say is that this filtering, you can be worried that the filtering of the A-grid mode, which gives damping on the free surface, essentially is going to, lead to energy loss of energy conservation, and it does. The question is how much damping do you induce by that? So there is again a more or less classical test case, which is just a Gaussian bump on a beta plane this time. So you get geostrophic adjustment to the beta plane balance or semi-balance, okay? And what you look at here is just the energy conservation of the scheme. So you start normalize the energy, start with one for all the models. The blue curves are from Frédéric Dupont's thesis in 2001, and that's result obtained with various finite element formulation with different combination of bases for the elements essentially, and also lumping or delumping. That's why you have delumped and lumped and so on. Okay, you can formulate a perfectly energy conserving and so on the C-grid. That's one of Sadurni's stream function formulation. Okay, so that's perfect. You preserve everything in this case. That's the black curve. And you see the various formulation, and that's the 2 GRS formulation here. There's one where I turn off the advection just to see what is the effect of the nonlinear advection term on the damping. Because of course the sum of the damping is due to the limiting in the advection schemes or the upwinding. Okay, and you see that most of the damping is induced by the A-grid correction, but it's still reasonable, say reasonable compared to these finite element formulations.
Stephane, do you know if the unavailable energy has been taken out here? One problem with the total energy metric is typically 99% of the energy in the system is unavailable.
Yes. Yeah.
And so if you can dissipate all of the available energy and still come up with a metric that says I conserved 95% of my energy.
It's a good point. I don't know. I'm not sure how you would do it. That would be interesting.
Right, so you have to find out what is the potential energy of the fluid at rest.
Sure.
That's the unavailable energy.
Sure. Yes.
And then compute the metric relative to.
So I guess this is. It depends on the way you compute the potential energy. So my reference state here is actually the flat free surface. So I guess my potential energy is only the available potential energy in this case.
Good. Right.
I think.
This is one layer.
I need to check, but that's the way it's defined. So because I only take into account the perturbation to the reference state, so that should be okay, I think.
This is a one layer problem.
So one layer,
So
one layer.
in one layer, it's actually okay. You can solve the problem.
Well, you could even
depending on how you.
Okay.
You could still take a reference state,
because
which
otherwise that bottom line would have dissipated significantly more than your available energy, right? The bottom line's down to 0.7 something.
Sure. But you're looking at
Okay. So you can apply. I mean, it was a bit all academic. We did apply to more, practical problem. That's tidal flow through. That's the North Island of New Zealand, the South Island, and there's quite, very complicated coastline just north there, and there's complicated. It's very active. You get phased. Basically the tide on this side and this side are in opposition of phase. You get really strong current to Cook Strait and things like that. So we did apply to that. I will just go really quickly through that. And what you generate is strong currents, and you shed eddies at each of these very sharp headlands. So you get a family of eddies. If you start resolving them, you can track them for a long time. Of course, their lifetime depends on the bottom friction parameterization that you use. So that's one of the unknown, but that's something you can do. Of course, you can do it because we track. Of course, the coastline is tracked at high resolution, but also the individual eddies are followed by the Quadtree mesh. Okay, and there is some evidence that these things are real. I don't know if you can see it, but you can see that this island, which is about 10 kilometers long, that's Wellington just here. You can see that it sheds eddies which are on the sides, which is comparable to the side of the island, which is more or less what we saw before. Also, you can see headland eddies being shed down there. It's anecdotal evidence is there. Okay, I'm just going to switch to a different formulation. So what's the problem with the first formulation? Well, one thing I don't like is that it's linearized. Okay, you may say it's okay because it's mostly, free surfaces are mostly linear in the ocean and so on and so forth. One place where it's certainly not linear is when you get to the coastline. So if you want to do wetting and drying properly, well, you need to take into account in some way the nonlinear terms, because that's the only way you are going to guarantee the consistency of essentially mass and momentum conservation near the coastline. So whatever you do, even if it's engineering approaches where you extrapolate, interpolate, they are only going to work because they are consistent in terms of momentum and mass conservation near the coastline also. And that's what the nonlinearities are about, really, in the evolution equation. Okay, so one way of doing this is to recast the shallow water equation as a system of conservation laws. Okay, so that's just let's say finite, a weak form or integrated form, if you want, formulation for it. So just have your conserved quantities there, and there is some flux through the surface, and there are also some source terms, okay, on the right hand side. And so your conserved quantities are the depths of water and the two momentum components, okay, and the fluxes looks like this, okay. So you have two parts to the fluxes. Of course, you have a pressure term here, and of course you have a momentum advection there. Okay, that's the two bits. So here you go. That's a system of conservation laws with source term. So okay, you can say I'm going to solve this system naively, let's say, and just compute these two terms. So the flux of mass and the flux of momentum separately. So just use an advection scheme or the same one or a different one for each of the bits. Then I will automatically, if I solve this, then I will get conservation, which is true. You will get conservation of both mass and momentum. But one thing you will not get is the higher order, I call them thermodynamic constraints, like the entropy inequality, the fact that the entropy doesn't decrease with time. Okay, it always needs to increase. That's what it is. You won't get that, and what this means is that when, for example, one place where this really matters is when you get shocks in the solution. Okay, so we get discontinuities, and in this case, essentially the entropy inequality, one way to see it is that controls what happens through the shock. Okay, so the speed of the shock itself is you can find, so the Rankine-Hugoniot relationship, if you want, you can find by using the entropy inequality. So if you have a scheme which doesn't use this condition, you are not going to guarantee that the shock propagates at the right speed. Okay. And all this, of course, is called thermodynamic because it's analogous. It's actually identical to the 2D compressible Euler equation for compressible gases, but with a polytropic exponent gamma equals to 2. If you do this, then you recover the dependency of the velocity as square roots of the density, square root of h. Okay. And the square root comes from the polytropic exponent 2. Okay, it's 1 over gamma. Okay. This problem is hyperbolic, so it has characteristic solutions. So the classical way to solve it is to use a classical way. Yeah, it's not the only one. Is to use good enough type collocated finite volume shock capturing schemes. And in contrast to the scheme I showed before, they are dissipative schemes rather than dispersive schemes. Okay, so what they do near the shocks, you have to do something near the shocks numerically, and what you do to stabilize the method is that you dissipate the shock rather than disperse it, which is what you would do if you don't take into account the entropy inequality there. Okay, so in practice I use an HLLC approximate Riemann solver. What this means is that, importantly, is that the dispersion relation is exact, whatever the resolution. So you don't have any problem when you go to very fine resolution. Your waves still travel at the right speed, okay? Because it's encoded in your approximate Riemann solver. Okay. So there are other issues with that, is that you get wetting and drying, so you have a density which goes to 0 on one side. Okay, that's not usually what happens for gas dynamics, or it can happen, but it's rare. So you need to adapt your schemes. That's what the C is about. It means contact discontinuity. So it's a scheme which can deal with contact discontinuity wave when the density goes to 0 on one side, which is what happens when you get wetting and drying. It's positive, which is an important thing. You want the water depth to stay positive, of course. And the important things too is that, which I didn't really talk about, is that you need to ensure, because you are now splitting the fluxes, the pressure terms into a flux term on the left-hand side and the source term on the right-hand side, which is your bathymetric forcing, you need to be careful to ensure balance, hydrostatic balance. Okay, and it's very, it's very similar to what you get, the problem you get if you do sigma coordinate models. Okay, you have to be careful in the way you discretize the pressure gradients. But that's a solved problem, and that's described in the scheme of Odus et al. 2004. And it uses explicit time integration. Okay, so why worry about free surface non-energy and shocks? I will just give an example, which is linked to tsunamis, which we have worked on. So you may think of tsunamis that are very linear because they have very long wavelengths. So in this example, you see the wavelength is 4 kilometers. Okay, the water depth is 1,000 meters. Okay, and the wave amplitude is just 1 meter. So it's a very mild slope. You're going to say, can't be more linear than this. Okay, and that's what happens for tsunamis. So what I plot here is two solutions. One, I think I can't remember which one is which, but I think the blue curve is the solution of the Boussinesq wave equation. Okay, so it's the dispersive correction, the first order dispersive correction to the shallow water equation. Okay, that's a third derivative of the velocity field, essentially correction. And the red curve is the shallow water equation. Okay, solution for that, and that's kilometers, and it tracks the wave as it goes. So you will see the kilometers go past, and that's what happens. Okay. So you see a soliton going this way essentially, and what you get, okay, the blue curve you see is dispersive. You get dispersion of the wave at the back. Okay, that's the Boussinesq equation, and then you get this nice solitary wave shape. But now if you look at the red curve, you see that we are at 60 kilometers. I should have carried on longer, but anyway, you see that the wavefront steepens. Okay, and it steepens in finite time. I mean, suddenly 100 kilometers. I mean, imagine 1,000 kilometers. This thing would be really sharp. And what happens, of course, is that your nonlinearities are weak, but they are always in the same direction. So the wave at the back is always traveling a little bit faster than the wave at the front. So eventually it catches up, and you get a shock. So in finite time, if you solve the shallow water equation, even for this very mild slope initial solution, you develop shocks. Okay.
I just need it clarified. The blue curve is the finite volume with the co-located.
No, it's not really linked to the numerical method. That's an exact. You can see that as an exact numerical solution. Okay, converged numerical solution. That's the blue curve is the Boussinesq wave equation. So you have this solved using any method you want. You can use finite difference in 1D. There's enough point that it's converged essentially. The red curve is the shallow water standard shallow water equation. But with a nonlinear term, with any solver you want.
So
it's really solved the shallow water equation.
So you get a better solution if you linearize your equations.
Yes, true, exactly. That's what saves people in a way. But the problem is that usually they don't say it, and they don't really necessarily know it.
So the thing that's kind of most wrong with the red solution is that you have this steepening effect because you've got one nonlinearity, but you've crossed out another nonlinearity. Basically.
Yes, if you want to.
If you actually solve the linear shallow water equations, then the red curve would just propagate further, and you get what is actually a better solution because
in effect you would get a better solution to the real physical problem.
Yeah.
Yes. But what you solve in effect, you need to know about this. You can get away with it.
The solution will be utter crap once you start it to show. That's the downside.
That's right, exactly. Yes, and when for tsunamis, of course, that's very important. You want to track that right up to the coast and so on. So, it's more subtle than it's more subtle. But essentially, if you say I'm solving the shallow water equations, the red curve is the exact solution. Okay, and then the next question is: are the shallow water equation appropriate to describe the problem at wide scales and so on? But you need to split the two. You can't really just say I'm linearizing everything and then it will be fine. Okay. Okay. So another example with rotation, people say, okay, but with rotation this goes away. Well, no, it doesn't. There is this nice paper by Bouchu, Le Sommet, and Zeitlin in JFM 2004 where they look at geostrophic adjustment of rotating 1D shallow water, 1.5D. Okay, so what you are looking at here is the free surface, and there is a zonal jet. Okay, I didn't plot the velocity; that's just the free surface. But essentially, you can see the jet is coming this way. Okay, and you fix the velocity profile of the zonal jet. It's a Gaussian bump in velocity. So of course it's not balanced initially because the free surface is flat. So you get geostrophic adjustment, okay, to something which looks a bit like that. You can imagine these shocks propagating away eventually, and then you get some profile which reflects the balance of your zonal jet. Okay. That's there are two numbers which control this problem. There is a Rossby number and there is a Burgers number. Okay. And that's for this particular combination. So yes, indeed, it's Rossby number close to 1, but there are many cases for atmospheric flows, for example, also for internal waves in the ocean where the Rossby number is close to 1. And what they showed is that you always generate shocks in the shallow water equation. So it always adjusts through shocks, okay? Even in rotating shallow water. So I think shocks are important. Anyway, okay, so you can test that. The numerical method I showed before, there's a nice, we talked quite a bit about test cases. So the nice test case, which is oscillations in a parabolic container, if you want to test whether your code can do wetting and drying. So just a parabolic bottom like this. And the nice thing about the parabola is that you get a solution where the free surface is flat, well, it's flat, it's a straight line, and your velocity only depends on time. It's constant in space. So that's how you can get an analytical solution for it, for the full nonlinear problem, because of course the velocity is constant in space, so your nonlinear term vanish in the momentum equation, so you can solve that analytically for the full problem. And that's with linear friction, so that's tau here is the friction coefficient for linear friction. And so you get an analytical solution for the velocity as a function of time, just decreases as a damped sine wave. And that's what you get for the free surface. So it looks a bit complicated, but remember just the intercept is that, and the slope is this thing. You see there's x is only there. Okay, so you get the straight line, and the intercepts move up and down to conserve mass. And this is the way the slope evolves. And this is based on Thacker work in the 1960s, but this paper with linear friction is Samston instancing 2006. Okay, so that's what you get for the velocity. So you get a nice damped sine wave, that's analytical numerical. You can get convergence, so you get second order, which is what we expect for the velocity, because it's essentially averaged over the whole domain. And that's what you get for the free surface position, so for the oscillation of the free surface. And different norms, so that's the max norm, and that's 1 and 2, or 1 and 2 and max. What you see that you get something which is between first and second order, which is not surprising, because what you get at the contact point, you have contact discontinuity, so in effect you have shocks. That's where the error is largest, is near the shocks, because your scheme has to reduce to first order, okay, near the shocks. So that's essentially the best you can hope for in terms of max norm convergence is order 1.
Stephane,
yeah?
in this solution of the boundary layers also, the fluid is in contact with the walls of the container. Will there be some boundary layers?
It's just it's average in the vessel. It's really shallow water. So the boundary layer effects, if any, are only represented through linear friction. So it's a much simplified. It's not a 3D problem. Of course, the 3D problem is much more.
You did have friction, which is why it was
damped. Linear friction. Yeah.
Which is why it was damped.
That's right. Yeah, the damping is through the linear friction.
And how uniform was you? You showed us the amplitude, but you didn't show us how uniform. Yeah. Did it stay uniform?
It's more or less at the contact points, depending on how you compute the fluxes, you can get fluctuations. So yes, you could do the.
But isn't that a good test as how much fluctuation do you get? One challenge.
Yes, it's the same thing. If you look at U as a function of space, you will get first order convergence for the velocity also, because the discontinuity in mass and momentum are converted the same order anyway. So yes, you will get similar. Yeah. Okay, so we can apply that to to real problems. So one thing we did is tsunami. So that's just an example of a reasonably old simulation. So that's 2004 tsunami, initialized with some realistic initial deformation. Oops, sorry. So the thing there is that I'm just going to show you how it looks. So the thing is that we adapt the mesh. The big squares are 100 kilometer square, okay, and we adapt down to 1 kilometer. And as you can see, okay, you can see that Sri Lanka was just 2 grid points at the start, and then now it's well resolved. The same thing, you can see the Maldives appearing there, okay, at the kilometer resolution. Of course, they are not there at the start. So we also reconstruct the terrain at the same time as the solution evolves. So you can see just before the wave arrives, it gets refined. You can see the Maldives are going to appear just there.
Very pretty, right?
Yes, it is. Yeah. No, we have comparison with inundation data and tide gauges and things like that. And
how do you compare? So one of the tough tests for this one is by fluke. Topex went over during the tsunami.
Yes, that's right.
How do you compare with the Topex track?
Yeah, it's comparable. I mean, there's nothing different to what people, well, if people who have been using shock capturing schemes, okay, or various schemes, we do, the test is that we do similarly. Yeah, there's no big difference really. It's the main source of errors in most of this simulation, when you resolve the problem, numerically properly, is the source. Right. That's really the largest one, and you can do any amount of tweaking to optimize that, but then it becomes a bit iffy because
there's a fairly big error term actually caused by what I think you did, which is assuming that the source all happens at once.
Yeah, which
it takes about 10 minutes if one into the other, which really
that's right. But that's not what you do if you look here. You can see the fault actually going in segments in this.
So that helps.
Yeah. Okay. So what does the adaptive mesh look like? It looks like that. So yeah, I just represented the color again is is the level of the Quadtree. So that's what it looks like. Okay, you can see the coast again being refined, and so the dark red is 1 kilometer and it's 100 kilometers. And of course we can do that at every time step. We do that at every time step. Okay, you can look at things like maximum wave height, and we compare those measurements and so on and so forth. Okay, one thing I want to go back to the scaling arguments. So what I look at here is the maximum resolution. Okay, the mesh size as a function of the maximum resolution. Okay, so of course if you did that on a regular grid, you just scale that x minus 2, okay, because you have 2 dimensions of space. That would be this scale. On an adaptive grid, can you predict how it's going to scale? Not really, so you have to do the simulation, which is just what I did there. Okay, I redid the same simulation with the same threshold for the error, which is what I showed before, an adaptation, okay, but using allowing maximum level of refinement finer and finer, okay? And that's what you get when you count the number of elements in the simulation. And well, the first thing to note is that it's still a parallel, okay, pretty close to parallel. And now the exponent is 1.4 rather than 2, okay? So the question is, what is this? What is this 1.4? Can you interpret that in some way?
Is that the right thing to do? Because if you hold the error metric constant and put in a minimum, you're kind of slicing through what you're going on, but everywhere else you still adapt just as much as you otherwise would have done.
Yes, that's right.
Is it not better to scale the error term?
Maybe. No, I'm not arguing that's what you should do in the end. I'm just looking at what this effect is. In effect, that's what you do when you use a regular Cartesian mesh. Is that usually you don't worry about how the error is distributed. But you say that I want to increase the resolution everywhere. It's going to decrease my error by some amount, in some areas, and it's going to decrease, essentially you're not going to get an error which is distributed uniformly over your domain. Okay, just the same sort of idea.
It'd be nice to have questions for everyone at the end. So we're nearly out of time. So if you could finish off as soon as you can.
Yes. So so there is a connection, of course, between this number and the fractal dimension of the problem. Okay. So a classical example of fractal object is a Sierpinski triangle. It looks like that. It's a true self-similar object. So you can have an exact definition, an analytical definition of its fractal dimension. If you compute it, so there is one which is called the box counting dimension, okay, where you cover the problem with small boxes, okay, and you count the number of boxes as you make the boxes smaller to cover this pattern. Okay. For a pattern which is truly self-similar like this, you can do this analytically, and you get analytically 1.6 for the dimension of this object. Of course, you see that's almost exactly what we do when you cover the tsunami pattern at some given threshold for error, okay, with the mesh. So you can interpret, in effect, the dimension we got as the fractal dimension of the tsunami wave. You can do better than this. This was the time average fractal dimension we looked at before. You can compute it at every time, so you can actually have the evolution of the exponent as a function of time. Okay, so it goes like this, starts like that. So it's fairly high at the start, and decreases to something which is almost close to 1, and then reaches more or less an asymptotic value at the end. So how can you interpret that? Well, at the start, you have quite a complex source, okay? And it's complex enough that its dimension is close to a full surface. Okay, so essentially, this is the dimension of a complex surface, because you have lots of peaks and troughs and stuff like that. then what you get is a collection of fronts. So why do you get a collection of fronts? Because if you remember, you sharpen the shock waves, and what you have essentially is resolved shock fronts, so lines. So you expect the dimension to get to 1, which is the dimension of the lines you are solving, okay? And then eventually you converge to a constant value, which is what all the energy is concentrated on the coastline. So this is the dimension, the fractal dimension of the coastline. In this case, it's close to 1.35, and by a fluke, really, it's almost exactly the fractal dimension that Mandelbrot found in his 1967 paper for the coast of Britain. Since then, people have found that it's very typical of coastline to have this type of fractal dimension. To illustrate the link between the scaling exponent of the adaptive method and the physical scaling of the structures. Okay. Unfortunately, I don't have time to show you the 40 slides more I have, so I'm just going to jump. Or maybe to this one. I'm just going to shoot this one, just to show you that it holds for a more complex. Oops, sorry. Oops, no. Sorry. Okay, so that's an example of a lock exchange. Okay, and you can do the same type of analysis. So essentially, look at the evolution of the in this case density field as a function of maximum resolution. Okay, and from that you can compute in the same way. Okay, that's the level of refinement. Okay, so you see that you refine close to the interface between the two phases, and again you can compute an effective fractal dimension from that. And the nice thing about it, so I can tell you a bit more if I have the time, is that you can actually explain it theoretically. You can actually find a theoretical explanation, so a link between isotropic turbulence theory, okay, and the dimension of this fractal line. And you find something, you find 1.33 without intermittency, you find 1.36. The interesting thing is that it's recovered experimentally. It's also what you get for cumulus cloud boundaries, okay? You get something which is close to 1.35. So again, because the physical scale distributions have specific scalings, if you use adaptive method, you can expect to recover this type of factor there. And coming back to my first slide, you can expect to change the scaling exponent of your cost function as a function of resolution. So not only change the prefactor, but actually change the exponent. And there's a link between the physical scale.
That's a cumulus cloud that lives in the 2D world.
Yeah, I went quickly through that, but it holds in 3D. It holds in 3D. It's actually the theory is 3D. So it's looking through slides. So you get 1.36 for the slice through it, and you get 2.36 for a full 3D thing. Just went quickly through that. Okay, conclusions. We can get accurate and fast solution for multiscale shallow water problems. I didn't show any of these things. So shock capturing schemes can be used to get consistent description of nonlinear terms, especially near coastlines, on collocated adaptive grids. I think that's important. And we are working on multi-layer extension of this type of schemes. Okay, approximate projection methods can be used to stabilize the computation of a grid discretization. There's this idea that the adaptivity changes the scaling of the computational cost, so actually this exponent, which is the important bit, rather than only the prefactor. There is a link between the physical scale distribution and the cost of adaptivity, so I think there is interesting question to explore there. I mean, you could use that, all the analysis that people have done in turbulence, for example, or of geophysical fields. And of course, there are many open questions. So, for example, what is the influence of anisotropic scale distribution on these scalings? And an important one is, can you extend these analysis if you use subgrid scale models? I mean, if you look at turbulence, for example, you know that a given subgrid scale model is valid if it's, let's say, homogeneous isotropic. Okay, what happens if you say, okay, now you have a metric for your adaptivity, which is now I can measure that it's homogeneous and isotropic, so I stop refining, okay, just at this scale. So that's going to vary depending on position, but what is the effect on that on the exponents I showed before? Thank you.
You mentioned your adaptivity criteria?
No, I didn't have the time. It's based on, well, there are various criteria you can use. So one criterion, the criterion I use for the tsunami is based on the truncation error, an estimate of the truncation error. So essentially the scheme is first order near shocks, or you hope so, and second order away from shocks. So if you estimate essentially the gradient of the quantity near the shocks, that's going to give you an estimate of your truncation error of your scheme. And if you can estimate the curvature of the field elsewhere, it's going to give you an estimate of the second order truncation error. So that's what we use to adapt the mesh.
And another question related, I think Hilary showed result with trying to predict where you should adapt. Are you using, let's say, a small time set so that doesn't happen, or are you,
I'm not sure.
are you trying to forecast where you should adapt?
Beforehand? No, we don't do that. The thing, I'm not sure. I mean, maybe that's.
You could do that easily by just saying, okay, here's where the threshold set. I should refine. I'm just going to refine more, and give yourself a couple of extra layers of.
Yes, but I think we could do that.
That's the standard way to do it with structured AMR.
Yes, but with maybe I'm not sure, but maybe in our case, because we adapt at every time step, we don't need to have a buffer zone in effect, which would take into account the fact that we are advecting something into a resolution which is not yet refined enough. Because you adapt at every time step, you actually follow even sharp fronts like shocks. You always advect them in a region which is already refined enough, just one step in advance. So that's the idea.
I have to make a comment on the Rien-Chow regularization, which I've used a lot, and often it seems to work very well, especially if you use a large time step, because then you're not resolving the fastest waves. But then it really helps to have some kind of upwinding, or but then when you have the upwinding, you're using the nonlinear terms to control the linear oscillations. But then you'll always find a case, particularly if it's nonlinear, and if you have a small time step where it just doesn't work. So I'm not so concerned about the damping of the Rien-Chow normalization, but more the fact that it's not sufficiently robust.
Well, if you have test cases, which I would be very interested in trying them, because we found it. When I say we have found it quite robust for certainly for.
But then you're also using that's also with the upwinding with the nonlinear term.
Sure. Yes.
Yeah. So then, if you, for example, I couldn't use it anymore when I was doing a flow over a hill. Because then your oscillations in the vertical direction, but no flow no mean flow in the vertical direction. So suddenly your upwinding can't control your computational mode.
Okay. No, I mean, I think it would be nice to convince people that it does work. It would be nice to find. Yeah.
Or to realise that it doesn't.
I think it does. I'm convinced it does.
So was I just?
I'm convinced it does essentially because there is such a large body of work in complex CFD problems where it works very well. And people have worried about things like.
They've always got diffusion and upwinding and.
No, I think some people in the CFD community are doing things very well.
Okay,
so you can't, there certainly are people who have, schemes which are too diffusive, but there are lots of people who are worried about having minimally diffusive, stable schemes combined with the grid and gives good results. So I'm not saying, it necessarily extend, but I'm just saying that gives me confidence that I think it should work also for barotropic or shallow water equations.
It works to some extent.
That one to two refinement works so well. It depends apparently that you keep the second order of approximation for smooth fields. So can you just describe how that happened? Because you use the finite volume technique, which for many simple application goes down to first order when the grid becomes irregular. So what is the kind of tricks you make? Can you just describe in one sentence or in
you need to define your operators so that they keep the order of accuracy at the coarse-fine boundaries. You need to be careful. I mean, the naive way of doing it would be to use a standard. I mean, if you look at stretched grids and you use your standard scheme without worrying about the size difference of the elements, of course the accuracy is going to degrade as you stretch more and more. The only thing is that you have to take into account the fact that your stencil become variable lengths. So of course, you need to take into account properly the size difference of the elements. Yes, if you define if you are careful to define the fluxes so that they sum up at course, but it's very simple to do.
Where the conservation of misery comes in is that it's co-located. It's definitely remain second order and some conservation problems, but it's co-located.
You don't have. I mean, we have another scheme which I didn't talk about, which is actually C-grid on the Quadtree. So it uses this idea that the velocities are now phase averages rather than volume averages, so it gets around this inconsistency I talked about before. So it's certainly possible to do C-grid also. So it's not a limitation of the Quadtree in itself.
Donna, did you have a...
Yeah, I was curious about how these off-tree methods parallelize, because I mean, it seems like you would have lots of communication. Is it, do you do sort of, I don't know, maybe you could say a few things about what you do? Or
it's not, I mean, I don't think it's not different from regular Cartesian grid. I mean, the way I do parallelism is domain decomposition. So and it's relatively coarse-grained parallelism in the sense that what we keep is on each processor we keep the root of the Quadtree. So what we have, I think you mentioned, somebody mentioned the forest of Quadtrees idea. This is very much what we do. Is that you have Quadtrees which are entirely contained within one processor. Okay, and you do parallelism at the level of one entire Quadtree. So you have lots of Quadtrees which are connected together. That works quite well. One of the limitations, and I think Rob is not here, but Rob talked yesterday about multi-level, and we do exactly the same thing, which is when you go up in the levels for the multi-level solver, then there is a stage where you only have one root of one Quadtree per element, so you can't coarsen further than that, or at least not easily, not in the easy way you have with the Quadtree. So we just stop there. That's our coarsest level. Of course, there is a balance. If you imagine something which is extremely parallel, then you will have one grid point per process. It's not multi-grid anymore. But that's a sort of compromise you have to make. Pardon?
How do you maintain load balance?
Can this be carried on
later? Why can't we do
I can show you. We redistribute all Quadtrees, Quadtree blocks.
Okay.
So it's balanced at the level of one entire Quadtree, not one element. So again, it's coarse-grained balancing and coarse-grained parallelism.
Coffee?
Okay.